what is the relationship between the cell potential, equilibrium constant, and the decrease in the free energy of a galvanic cell. We know in a galvanic cell we can convert chemical energy into the electrical energy. Now, what is the relationship between these three properties of the cell? Here we have a galvanic cell which is made by connecting the zinc electrode with the copper electrode, and under the standard conditions this particular galvanic cell has a voltage of a 1.1 volt, which is actually the standard EMF of the cell. So you can say this is the standard EMF of the cell. And we have also learned as per the Nernst equation that when you change the concentration of the two electrodes, it will change the the electrode potential also. And the EMF of any cell, EMF of the cell is actually equal to the reduction potential of the cathode minus reduction potential of the anode. So if the difference here is more, if the difference in the reduction potentials of the two electrodes is more, the EMF of the cell is more. This is what we have learned previously. Now in this example, we have the zinc electrode which acts as the anode, means the electrons are lost from the zinc electrode and they move towards the copper electrode, which is a cathode here. So with time, what happens, the concentrations in the two electrodes keep on changing, and that will change the reduction potentials. And when the cell is the dead, means it doesn't produce any more current. So that is basically the state of an equilibrium, right? So basically at the equilibrium state, the two electrodes have the same reduction potentials, right? The reduction potential of the cathode will be equal to the reduction potential of the anode. That is what we call as an equilibrium state. And at that time, this particular cell will have a zero EMF. And as per the Nernst equation, it says the EMF of the cell will be equal to the standard EMF minus RT by NF ln the concentration of the the ions in the anode divided by the concentration of the ions in the metal ions in the cathode here. So when these concentrations change, that will change the EMF, right? And when the system, when this particular cell is dead, right, that means it doesn't produce the current. So basically we can say at that point the reduction potential of the cathode is equal to the reduction potential of the anode, because by with the time what happens inside those two electrodes, the reactions are going on, and that suppose the copper ion concentration here decreases, the zinc ion concentration increases, and we know that the cathode has a high reduction potential and the anode has a lower reduction potential. And when the concentration of the copper ions decreases, because the copper ions gains electrons from the metallic copper, the copper ion concentration in this electrode will decrease with time, so that will decrease the reduction potential of the the cathode here. Similarly, when the zinc is undergoing oxidation, the zinc metal, it dissolves into the zinc ions and the electrons flow through this wire towards the cathode. So the zinc ion concentration in this cell increases, and with the increase in the zinc ion concentration, the electrode potential also increases, the reduction potential of the zinc also increases. This is the thing that we have discussed in the Nernst equation for the electrode potentials. In that case we have learned that when you change the concentration in the two electrodes, it will change the electrode potential. And you can see here, when the copper undergoes reduction, the copper ions decreases, and therefore it will decrease the reduction potential of the copper, which is now here as a cathode. So it means that with time the reduction potential of the copper will decrease, okay, it will decrease, and that of the the zinc will increase, right? The difference is actually the EMF, right? That is the cell potential. And when we have the standard conditions, under the standard conditions they have some values, we have a higher this reduction potential of the cathode, and the anode has a less reduction potential, so the cell is producing the current. But when the system is under equilibrium, means the two electrodes has the same reduction potential. You can say the reduction potential of the cathode, in this case it is the copper, will be equal to the reduction potential of the anode, right? That will be equal to the anode. That means the EMF of that cell, of the cell, will be at that time, it will be the zero, right? It will be the zero. So when this particular cell is under the equilibrium, means this EMF of the cell will be 0, right? The EMF of the cell will be 0. So therefore you can rearrange this equation at the equilibrium. At equilibrium, when the EMF of the cell is 0, we can say the standard EMF of the cell will be equal to the RT by NF ln the concentration of the zinc by the copper, that is K. That is the K. Why this is the K? Because this is the equilibrium situation, right? We have the equilibrium constant. Now once the system attains the equilibrium, the concentration of the zinc and the copper ion in the two electrodes, it doesn't change further. It keeps the constant, right? It now remains the constant. It doesn't keep on, it doesn't now change, because now there is no more cell current produced and there is no change further. So at equilibrium, when the two electrodes have the same reduction potentials, EMF of the cell will be 0, and this ratio of the zinc ions by the copper ions, it will not change further, it will remain constant, right? This is the equilibrium constant. So this is the EMF of the cell. So it means that from this equation you can find the equilibrium constant of a reaction of a particular cell, of a particular redox reaction. You can find its equilibrium constant from its standard the EMF of the cell. If you know the E0 of the cell, you have the RT by NF. R is the constant, temperature is the the temperature at which the cell works. We have normally the room temperature 25 degrees Celsius, and F is the Faraday's constant, and N is the number of the electrons that are being transferred in that reaction. So you can find the K value of a cell, and this K, this equilibrium constant of a particular cell, actually tells us about the extent of the reaction, right? It tells us about the extent of the the reaction up to which work a cell can produce the current. Now we have also learned that this delta G, which is equal to the which is the Gibbs free energy, the decrease in the free energy of the system will be equal to minus NF E0 of the cell. This is what we have learned in the previous video, that the maximum work that we can obtain from a cell will be equal to the minus NF E0 of the cell. So delta G indicates the decrease in the free energy of the system, which actually is the maximum work which you can obtain from a particular cell, and this is what we have learned in the previous video. We have discussed there in detail. So means that if I try to let's say we're gonna use this value here over here, right? E0 of the cell. So I can say this delta G will be equal to minus NF E0 of the cell, right? NF E0 of the cell. So I can put the values here, I can say NF, and this will be E0. So I can say this RT by NF, right? This is RT by NF ln K value, and you can cancel out these two, and we can see the delta G is equal to the this will be equal to the minus RT ln K, negative RT ln K. And so this is the relationship between the delta G value and the decrease in the Gibbs free energy and the K value here. So we can relate the three important properties of a cell: the EMF, the standard EMF of the cell, with with the delta G value here, the change in the Gibbs free energy, the maximum work that we can obtain, and you can relate the this delta G with the equilibrium constant of the cell, and you can also relate it with this one, the EMF also. The delta G we know is equal to the Gibbs free energy is actually minus NF E0, so you can say it will be equal to negative NF E0. So you can find the maximum work, the decrease in the free energy of a system, from its standard EMF of the cell, and the standard EMF of the cell will be related with the the K value, the equilibrium constant of the cell, by this equation number 1, which is the E0 of the cell is equal to the RT by NF, right? This is RT by NF ln K here, and you can find the delta G from the K value also. So this is the last equation that we have got here. The delta G will be equal to the minus RT by RT ln K, right? RT ln K. So these are the three important equations which we are going to use in the next couple of videos. So we will do some some questions, some problems, right? We'll do some numericals on these equations. Hope you got it. Thanks for watching the video. Bye for now.